Okay, so we have learned about stresses, we have learned about strains, and today we are going to learn a little bit on how to relate these stresses and strain. Today will be mostly the understanding part of the class. Next class onward, we'll get into more details of this stress strain relationship. So this stress strain relationship is known as, in mechanics, is known as constitutive relationships. Okay, and they are purely properties of the materials that you choose. So when you choose an aluminum material, or when you choose a steel material or a wood material, the material properties that will define those materials, the properties that will define those materials are part of these constitutive relations. Okay. So therefore, this part of the course is very important to understand. And also you should know how to apply these things, this understanding, into different kinds of problem that we will solve or we will face in our 4-year undergraduate course. So what I'm going to learn here is, first we are going to learn stress strain relationship. And that stress strain relationship will depend on material properties like Young's modulus, shear modulus, bulk modulus, moisture ratio. Okay. So those things also you should learn. So these are the terms. We will define them as we go along in the class. Maybe in another 2-3 days we will define all of them, but we need to know what these mean. Some of them already you know, probably Poisson ratio already you know, bulk modulus maybe also already you know, but Young's modulus and shear modulus is what makes the most part of our strength of material course. Okay, so these two are very important to know, and you should also know how to find that, one thing. And second thing is, how are they used. Then we will learn about Hooke's law, okay, and generalized Hooke's law. So Hooke's law and generalized Hooke's law, we'll learn it for 1D members, and then we'll learn for a 3D, all three directions that we have. Then we will learn from these three-dimensional systems, how to reduce them to a plane stress or plane strain condition. This is very important. This demands a little bit of more understanding, and also it's very important in the sense there are a lot of questions that can be made from plane stress and plane strain conditions. Okay, and that also makes your solutions becomes much easier. In many of the problems, it makes your problems easier in engineering sense, and solutions are simpler. Now this part of the slide tells you, we have seen this slide before, we are going to see today a little bit more details. We have learned, we know what are external loads. External loads are loads that are given onto the structure, that comes from the environmental factors like wind, it can come from earthquake, it can come from ice load, it can also be given loads like live load. Okay, a bridge can have a live load, then there can be a train load on a railway bridge. All those things becomes external load. Now these external loads are converted to internal loads to understand the mechanism how the load transfer from one point to another point in the structure itself. So if you have a beam, you know these internal forces are BMD and SMT, right? And if you're an axial member, you have to draw an axial force diagram. So internal force diagram you have to draw. That's the internal force. From that internal force, we use free body diagram to find that internal force. From that internal force, we find stresses using differential equations of equilibrium or governing equations of equilibrium. We understood how to find stresses in different kind of members with given internal forces, right? And those we call it as stresses. Once we find stresses, and we know there are at any point in a 2D material, the stresses are 3 unknowns, right? Sigma x, sigma y, and tau x, right? Whereas for a 3D member, it will be 6 of them, right? Sigma x, sigma y, sigma z, tau xy, tau yz, and tau zx, 6 of them, right? And you can represent them in a matrix format. We also learned how to get from deformation to strains using strain deformation relationships. We learned it, right? Strain deformation relationships are epsilon ij is equal to del uj by del xi plus del ui by del xj, right? And overall there is a half. So this is what was the strain relationship. strain deformation relationship. But we have missed somewhere this relationship, how to relate stresses with strain. So this is what is called constitutive model or material model that relates stress and strain. Please try to understand that deformation is geometric phenomena. It's a deformation, right? It's a kinetic. Uh, kinematics of the member or the kinematics of the material. Okay, so it comes from the kinematics, the deformation. We did not use anything related to load here while doing deformation to strain, right? This is independent of load. Whereas from when we move from internal forces to stresses, we looked into loads only. We did not look into whether there is a deformation in the material, it's a large deformation or it's a small deformation. We never looked into all those things. Okay. Now, these are the two different directions of movement. So we were talking about finite elements. These are the two different ways of looking into materials finite element also. So either you do deformation based or strain based formulation, or you do stress based formulation. Now, what relates both of them together is called constitutive relationship. Once you know constitutive relationship, you can see the complete picture of how deformations and loads are related. Okay, how to get deformation from given loads on a structure, and how to get loads from given deformation on a structure. Okay, right? So these are the two things that are necessary when you solve a problem, and that will come from the material model. So that's very important. When we move from internal forces to stresses, we did not say what kind of material it is, right? Did we say? We did not say. We said the kind of loading it can have. It can be one directional loading, it can have three directional loading. That is what we discussed. When you move from deformation to strain also, we looked into either it's a 1D material, that means one directional deformation is there, or a three directional deformations are there. In that case, you will have 3D strain, right? We discussed about that, but we did not discuss what kind of materials we're looking at. Are we looking at aluminum materials? Are we looking at steel? Or are we looking at wood, right? If you're looking at different materials, these deformations should be different. We did not talk about that, right? So today is the class where we're going to discuss on the materials itself. How materials makes difference between load and deformation relationship. What are the roles that are played by materials when we look at stress-strain relationship? When we look at the failures of the materials, right? Those all are we're going to be discussed in the next 2-3 classes. Okay. When we talk about 1D uniaxial material, we call it uniaxial. That means there is only one axis to the material. Okay, this is called uniaxial. When we say biaxial, there are two axes. Remember, this is a biaxial stress. Okay, and triaxial is this is triaxial, right? So when we talk about uniaxial, that means only one directional stress or one directional force or one directional deformations, whatever we want to say, is there. It's called uniaxial. So a material will have, let's consider a structure like that, again a rod or a bar member at point A, and you give a load P with the cross-sectional area A, so you get this as its stress, right? Normal stress. We call it sigma x on both sides. And it comes from the load as we discussed. And then there is a deformation from which it comes the strain. Strain will also be, since this is an uniaxial, there will be only one directional extension in the material. Since there is a tensile force, so there is an extension here, and this is called normal stress. So this is sigma x and this is epsilon x, right? The same material can have shear also if you have a force that is transverse to it, right? Or if you take a cross section that is inclined. So shear force V provides a tau xy, and that will give you a rotation. Right? This is also, so this is the stress part and this is the strain part. That's what we just discussed in 1D. Now, how do you relate them? How do you relate this stress with this strain? How to relate? How to relate sigma x with epsilon x? Okay, that's a question we need to answer. All right. So when we talk about this, we need to know materials proper. Yes, Karthik, any question you have? see. Okay, I muted it. Sorry, Karthik. Okay, now the relationship is provided by this. What we assume is, let's say we are looking at very small deformation and very small stress in the material. When we talk about a very small deformation and very small stress, we say that they are linearly related. Okay, please note this is for small strain and stress. Okay, we call them they're linearly related. When we say they're linearly related, we use a constant of linear relations, which is called E. Okay, but we will tell what is E. What happens when you have a material and when you start straining the material? Let's say I have this material and I start pulling the material like this, right? What will happen? The material will show if the material is ductile. You will say what is the ductile, what is the brittle material a little later. If the material is ductile, it's going to show up a relationship. The relationship is as we increase the strain in the material, the stress goes up. This is the stress axis, this is the strain axis, and it will show a very nice linear relationship. It will go up like this, and after a certain strain, it will have a kink here, and then there will be a flat region, flat with respect to stress, and then it will again grow up, grow up, go up, go to a maximum value, and then the value will start failing, and suddenly it will show here at this point, it will show a failure, complete failure, and it will fall like this. Okay. So when we are in the small region here, very small strain region, it behaves linearly. Material properties, experimentally, if you see, it behaves linearly. And that part is what we are looking at. And that's relationship where stress is linearly related to strain is called Hooke's law. Okay. So this is called Hooke's law. We will talk about this a little bit more maybe in the third class, but this is what is Hooke's law, where we call that stress in a material is proportional to the strain in the material. And the proportionality constant E is called Young's modulus or modulus of elasticity. How do you find E? You take 2 points on this curve, and then you use this formula sigma 1 minus sigma 2, or sigma 2 minus sigma 1 divided by epsilon 2 minus epsilon 1. That's how you find it. Or you can find this angle and take tangent of that angle, gives you E. Okay, this E is completely a material property. It's purely a material property. It depends on how the material is oriented, material fibers are oriented, what material you are using. If it's a man-made material, a composite, then orientation of the fibers of the composite becomes important. So it's completely a material property, and it's called Young's modulus or modulus of elasticity. Okay, and it's a strength. The strength is affected by this E can be affected by alloying, heat treating, or strain hardening, or various like composites. You have fiber orientation. Based on that also you can change it. For some material the values are given, you can see here. For steel it is 200 GPa. You should remember this as an engineer, this value. At least for steel, aluminum, wood, you should know. Okay, steel is 200 GPa, aluminum is 70 GPa, wood is around 10 GPa. So wood is, as you can understand, wood is of lesser strength than steel, and aluminum is lesser strength than steel but more than wood. Okay, so you should remember these things. So therefore, a same material of same geometric dimension, steel is much more difficult to break than a wood. Okay, so this is the strength of the material. This is where the strength of the material comes from. All right, so we just saw how do you get this curve for a ductile material. So can you tell me now, this is a ductile material or a brittle material? This is a ductile material. Okay. It shows a proper yield point, upper and lower, and it shows a proper necking here and a flat region. If I had to draw on the same curve a brittle material, it would have been something like this. Not that far, sorry, not that far, like this. Okay, and the linear part, if you take this linear part, is what we deal with, and this linear part is called proportionality limit. There is a limit here which is called proportionality limit, where after which the proportionality goes, so you will not have any linear relation between stress and strain. This part is under the purview of Hooke's law, and that's where we design our members mostly, unless specifically we design for plastic region. This part is also called elastic part or elastic region of the material because the behavior is elastic, right? Linearly elastic. So this part is where the Hooke's law is valid. This is what we have shown just now. This is a test. This is there in Professor Arukirajan's lab. There is a test specimen. You see, this is a different kind of test specimen because this is not for steel. This is for, I think, polymers and fibers and composites. So a composite material will be something like this. So that's the test specimen. This is the upper handle. This is the lower one, and it automatically gives you all the details that are necessary. Okay, you don't have to put a strain gauge here to measure it. You can always put, but not necessary. Right. So there is a length which is called gauge length. We just found that gauge length, and you can see there is a necking happening here, and then there is a break. Okay. Right. This is not a steel material, as you can see. This is a ductile material. This is a steel because there is a cup and cone formation happened here. There are various different kind of specimen you can have. You can have specimen, dog bone specimen, circular dog bone specimen like this. You can have flat specimens like this, but all of them should go through a same standard, ASTM standard, where the gauge length is fixed. The fixed part is also fixed, how much it has to go inside to be holding, and all those things. Okay. Now this is what we have seen, right? You can see there is a cup and cone formation here. This is the cone part, and this is the cup part. You can very clearly see, this is taken from our lab probably. Very clearly you can see the cup and cone when you do this experiment in your lab. Very properly. We do both for steel as well as for aluminum in our lab experiments. So you can see both cup and cone and a state failure. Now in plastic, you can see necking very easily, as can be seen here. You see, necking is when the area starts reducing, the diameter starts reducing is the start of the necking. Okay. All right. So this is a proper, stress strain curve. This is not a force deformation. This is a stress strain curve. Okay. There will be an elastic region where it will be straight. This is a proportionality limit here, up to which it will be proportional. The stress strain will be proportional. Within this zone, if you leave the material, if you leave the loading, the material will come back to its initial zero configuration. Okay, what I mean again, I'll tell. If you are in elastic zone and if you stop loading the material, that means if you unload the material, the material will come back to its zero position. Okay, as if there was no load given to the material. But if you cross this elastic limit, go to the plastic portion of the behavior, if you leave the load, the material will not come back to its initial position. It will come back to somewhere here where it will have a residual deformation and residual strain left in the body. All right. So that's the difference between elastic and a plastic limit. So if you take plastic, you pull a little bit, as long as it's elastic, it will not show any permanent deformation. But if you pull it like this, what I have done here, then you will see there are permanent deformations and it doesn't go back to its initial configuration. For rubber, if you pull it, you can go a longer length and you will see that it comes back to its original configuration, right? So this part is called the elastic part. So within elastic zone, if you load the material and leave it, it will come back to its zero configuration. But once you cross the elastic zone, you go to the plastic and leave the material, you unload the material. Once you start unloading, it will follow the initial curve, initial straight line, right? Initial slope, but it will not go back to zero. So there will be a permanent deformation here, permanent strain in the material. Okay. So this is the yield stress, and then this is the flat region. And then there will be again increase. This is called the ultimate stress. And then it will come to a point where the failure or the fracture happens. This is a fracture or a failure stress and the material fails. Okay. This diagram, the below diagram, is called engineering stress strain diagram, because here we divide to get stress with the initial area. Okay. The original area is used to divide to find the stress in this zone. But you can see that the stress, the area starts changing when the necking starts, right? When the yielding starts. So the area starts changing. And as the area starts changing, if you divide with the original, if you divide with the real area, that means the changed area, you will get another curve which is like this. This is called true stress strain curve. All those details you will get in the book if you read this. True stress strain curve, and this is called engineering stress strain curve. Okay. This diagram is very important for you to understand and very important for you to draw whenever asked. Few different materials will have different kind of curves. So low carbon steel will show a curve like this. We have seen in the experiment. Aluminum also we saw something like this. There will be some brittle material will not go up to this. It will only show up to this. Okay, rupture here itself. All right. Okay. So its ultimate state is where it's going to fail. It will not show any yield, and neither it will show any necking or anything. It will just break. For example, chalk. If you pull, it will not show anything, but it will break suddenly. Okay. Now, 0.2% proof stress also we discussed that for materials where we don't see a proper yield point, many materials will not show proper yield point. Okay. In that case, what we do, we take 0.2% of strain, okay, and draw a line parallel to its initial slope, and wherever it touches the curve, if I take the stress at that curve, it's called 0.2% proof stress. Okay, this is how you can determine stresses for aluminum alloys or aluminum where you don't see a proper yield point. This is also a question, very important question, which is asked that if you don't see yield point, proper yield point in a material, how do you find its yield capacity, right? So yield capacity is obtained using 0.2% proof stress. Stress strain diagram is shown, and as I said in beginning that many of the brittle materials, okay, will not show same value of or same capacity under compression and under tension. So you can see there is under tension, it is a very low value for concrete, very low value, where it for compression it shows very high value, how high strength capacity. Okay, so these kind of materials are very useful to make columns, because columns are mostly compression elements, right, but not tensile elements. So these are used if you know that your structure is going to have compression on that side, no, never it will have a tension, for example columns, then you have to use those kind of materials because they are very good in compression. Okay, here I'll stop. We'll discuss about these things in the next class, or you can go through the book. These are definitions only. What is called modulus of resilience, what is called modulus of toughness, and what is called stronger material, what is called strain energy. We'll discuss about strain energy a little bit more in the next class. These are a few strain diagram. So as long as you're in elastic region, it will come back, but once you cross the elastic region, it will not come back, it will come here, and there is something called residual strain that will remain in the material. Okay, and that you will not get recovered. So you will only get recovered only this part of the elastic. So this is also used for strain hardening a material. We'll talk about this also in the next class a little bit more. Okay, few curves. Yeah, with that I'll stop. Okay, we'll talk about these things in the next class.